All right, now we're taking a look at 5.2, the unit circle, focusing just on sine and cosine. So a couple of reminders. If I were to draw, let's say, a circle, where let's assume that the center is there at the origin, and I were to create some angle theta in standard position, we could also create a right triangle where our radius is the hypotenuse of that right triangle. The x coordinate is the length of one of the legs, and the y coordinate would be the length of the other leg. In other words, this point here would be the point xy on that circle. A couple of other things to remember when we're over here in quadrant 1. Our x value is positive and our y value is positive. In quadrant 2, our x value is negative and our y value is positive. Quadrant 3, x value is negative, y value is negative. And then last, in quadrant 4, our x value is positive, but our y value is negative. So as we're working with the sines and cosines, knowing what quadrant an angle is in will help us to determine the signs of the values we're looking for. So let's remind ourselves of the definitions of sine and cosine. Again, being a definition means, yes, it is something you have to memorize. So when we're looking at that circle, that theta on the circle there, the sine value of that angle, we'll call it theta, is the ratio of the y value divided by the radius. Cosine is the x value divided by the radius. So if you think about the unit circle, when the radius is 1, you would have sine theta equals y and cosine of theta equaling x. So when we're referring to an xy coordinate in a plane, we can also refer to it in terms of the angle in standard position. So that x value would be cosine of theta and the y value would be sine of theta. So since they represent the x and y coordinates, we can determine the quadrant it is in based on the sign and vice versa. So in example 1, it says if the cosine value is positive, greater than 0, and the sine value is negative, less than 0, which quadrant is the angle in? So again, remember cosine is the x value. X's are positive here and here, but the y value is negative. Y's are negative here and here. So we are in quadrant 4. For example 2, if the angle theta is in quadrant 2, what is the sign of cosine theta and sine theta? So again, we're up here in quadrant 2. Since cosine theta is in reference to our x value, then it's going to be negative. Our sine theta, represented by y, and in that quadrant, our y is positive. Now, we can use the equation of the unit circle. Sorry, this probably should have been on the next page, but we can use the equation of the unit circle that we talked about in 5.1, the x squared plus y squared equals 1, and now we can substitute sine and cosine. X is cosine, so we can write that cosine squared theta plus sine squared theta equals 1. Now, you may be wondering why I put that square there. So let's make a little bit of a note over here. Whenever you have a trig function like cosine theta, you don't want to put the squared on the outside because it kind of looks like, well, is that theta squared or is it the whole function squared? So instead of putting everything in parentheses, They just say we are squaring that function value at that single theta. So just make a note that when you're squaring a function, you put it in between the function and the angle. So since the equation of that unit circle, and also think about the triangles that we were building inside the unit circle, this is known as the Pythagorean identity. Remember, we have a squared plus b squared equals c squared. And we're going to be using this a lot. I call this identity the granddaddy. It comes up a lot. So let's take a look at this example 3. If we have cosine of theta equals 2/3 and theta is in quadrant 4, so it being in quadrant 4 tells me that the value of sine of theta is going to be negative. So we need to find the value of sine of theta. One of the things I want you guys to realize is right now they're not asking us to find theta. They're not asking us to find the angle. They just want to know that function value, the sine value of that same angle. So we can use our Pythagorean identity. Again, that states cosine squared theta plus sine squared theta equals 1. I know cosine squared theta equals 2/3, so we're going to take 2/3 and square it, plus sine squared theta equals 1. If we square the 2/3, we get 4/9. Now we need to solve for our sine squared theta, so that gives us a 1 minus the 4/9. If we get common denominators, that 1 becomes 9/9, minus 4/9 gives us 5/9. So sine squared theta equals 5/9, and now we need to take the square root of both sides. So taking the square root of a square, we just get sine theta. And on the right-hand side, we get the square root of 5, but the square root of 9 is 3. But remember, when we take the square root, we have both a positive and a negative. So we have to recall our sine theta is in quadrant 4, which tells us our sine value is going to be negative. So we make that a negative square root of 5/3. So in this first rectangle here, we're focusing on a 45, 45, 90 degree triangle. So we have a radius of 1. Our x value would be rad 2/2, and our y value also rad 2/2. So our sine value for 45 degrees is our y value of rad 2/2. Same thing for cosine of 45, it's just the x value of rad 2/2. Our 30, 60, 90 triangles, which we did back in section 1.0 point something, sine value again is the y. So that's our 1/2. Cosine values are the x, rad 3/2, because again, we put our radius as 1. And this is true anytime your hypotenuse there or your radius is 1. If your radius is different, your radius numbers will just divide out. It will always reduce to these same values. Sine of 60, sine is our y value, rad 3/2. And cosine is our x value of 1/2. So notice how they flip-flop. So now we can actually fill in the rest of our unit circle in quadrant 1 if we haven't already. So we will need to know the sine and cosine values of all of our special angles, which will include the 30 degree, which again is pi/6, 45 degrees, which is pi/4, and our 60 degrees, which is pi/3, because everything else will have a reference angle of one of those 3 if it's one that we're supposed to know the exact value. And we also need to know the quadrantal angles, the ones that fall on the axis, 90 degrees, which is pi/2, 180 degrees, which is pi, 270 degrees, which is 3 pi/2, got my degree symbol, and then 360 degrees, which is 2 pi. So let's do some examples where we're using reference angles and the values of the sine and cosine functions that we know. So suppose we have a theta of a negative 2 pi/3. Let's figure out what that reference angle is. we're in radians. So we've got pi here or 2 pi here. We have 3 pi over 2 here. So if we're going a negative 2 pi over 3, we would have 1 pi over 3 here, 2 pi over 3 here. Remember, it's negative. So it goes clockwise, negative 2 pi over 3. We're wanting to find this angle here. So if you've got 1 pi over 3, 2 pi over 3, in order to get 2 pi, we need one more pi over 3. So we have a reference angle of pi over 3. Now, what quadrant is that in? That's in quadrant 3. And we're wanting to determine the sine of a negative 2 pi over 3. It's going to be the same as our pi over 3. So recall that the sine of pi over 3, which is our 60 degrees, okay, that's the larger of those triangles. So that y value is going to be a rad 3 over 2, but we're in quadrant 4, so that makes it negative. So just real quick, off to the side, what did we just do? Pi over 3 is the same thing as 60 degrees. We knew that the sine of 60 degrees is rad 3 over 2. So it's going to have the same y value as its reference angle. The only thing that is different might be the sine. So since it's in quadrant 3, we know the y value, which is attached to the sine value, is negative. All right, let's do another one. Let's do the cosine of negative 2 pi over 3. Again, for both of these, the reference angle is a positive pi over 3. So the cosine of pi over 3, we know to be 1/2. But since we're in quadrant 3, we know that it is negative because all of our x values, x goes with your cosine, all of those x values in quadrant 3 is negative. So example 5, we want to use our calculator to find the following trigonometric functions and round our answer to 3 decimal places. So we need to show how to put our calculator in the correct format. All right, so we are asked to find 2 different trigonometric functions. Part A was the cosine of 112 degrees. And then part B was the sine of 3 pi over 7. So let's do the first one, cosine of 112. If you go down on your calculator and click mode, you might have a lot of options here. It might look a little different than mine, but it should be similar. Scroll down until you see the words radian and degree. Well, we want to be in degrees. So we're going to scooch down over there where it says radian. I'm going to highlight the word degree and hit enter. That changes it to degrees. And then I'm going to go back and just hit quit, second function quit, or clear. And now I can find the cosine of 112 degrees. So we click on the cosine button. We type in 112. You can close the parenthesis if you want to. Hit enter. And that will give us approximately a negative 0.3746. Your homework, your quizzes, as well as the exams that I'm going to write out should tell you how far to take out that decimal. Now, if we're to do the second one, we're assuming that we are working now in radians. Yes, we see the pi, but remember, we don't have to see the pi for it to be radians. The real clue is the fact that there is not a degree symbol. So we need to change our calculator back into radians mode. So we go back down to mode, scroll down to where it says radian, hit enter, and notice it unhighlights the degree and now it's highlighting radian. And we can hit clear or second function quit. Now we can put in sine value of 3 pi, so 3. Notice you have the pi here up above the caret. You really want to put in pi and not just 3.14. Otherwise, you have to round on an estimation. So all of that divided by 7, and then hit enter, and we get approximately 0.9749. All right, guys, that's it for 5.2. If you have any questions, don't hesitate to contact me. Talk to you soon. Bye.